I am now under the assumption that you can all see the presentation.
Yes.
Okay, awesome. So thank you everyone for joining the presentation. I will be telling you a little bit more about my research, which is on the modeling of exoplanet atmospheres. So I start by showing actually a similar picture to the one that Professor De Freire has shown last week, where he plots all the known exoplanets on this diagram with respect to orbital periods on the x-axis and then the radius. And why do we do that? So we have a bit of an overview of the exoplanet population. More than 4,000 right now are currently known. And I always find it helpful to always plot on this diagram as well the solar system planets. And then you can see that here, Mercury, the closest planet to the Sun. And you have here Venus and Earth, who are similar in size, Mars a little bit smaller, then Jupiter here, and all the other planets, they don't fit on this diagram anymore. So you see that actually most of the planets that most of the exoplanets that we know are on shorter orbital periods than Mercury is. So this is, of course, due to the detection techniques that we use to find these planets. And you also see that there is a quite big group here that is Jupiter-sized and very close to their star. And this group we call the hot Jupiters. And this is the group that I'm interested in the most because they allow for the easier detections of their atmosphere. And why would you want to detect or study the atmospheres of exoplanets? Well, for me, there are actually three big reasons. The first one has to do with life and habitability. So, of course, one of the end goals of exoplanet research is to find extraterrestrial life. We will not find them on hot Jupiters probably, but more on rocky exoplanets. But now the hot Jupiters are accessible for atmospheric detection. So this is a good place to start, I would say. And the atmosphere impacts a lot of factors that could be important for life, such as the climate, temperature, clouds, for example, to shield from radiation, stuff like that. And it also allows us to search for biomarkers, and these are gas species that you can find in the atmosphere that might hint at the presence of life on such a planet. A second reason could be to understand or to research the formation history of planetary systems, because the atmosphere holds chemical information, compositional information. And the composition of planets is, of course, linked to how they are formed, what material they accreted when they were in the protoplanetary disk. And this is linked to the mechanisms by which they are formed. So understanding the atmospheric composition can also lead to understanding of the formation of these planets, the migration history, the timescales at which this can happen. And finally, studying exoplanet atmospheres might also teach us something about our own Earth, because of course we on Earth, we also have an atmosphere, but it's not a good idea to try to do experiments with it. So we have climate change now, we are experimenting with the atmosphere and pumping CO2 in it, but maybe that's not a great idea to experiment with our own atmosphere, and we should focus on other atmospheres and use that as a sort of cosmic laboratory to really find out what types of atmospheres are there or how can atmospheric evolution continue. Then a little bit more on how the atmospheres of gas giants, or basically mainly hot Jupiters, are studied. So I already said hot Jupiters are the most suitable because they have low surface gravities and because they have high temperatures. And both of these effects act as forming basically a thick atmosphere or a very extended atmosphere. So there's quite a lot of signal to detect there. For these planets, unlike the techniques that we heard about last week in last week's seminar. We cannot use coronagraphy, for example, so no direct imaging. So we have to separate the light from the planet and the star in a different way. And there are, I would say, two main techniques to do that: high resolution spectroscopy and transit or transmission spectroscopy. And the high resolution spectroscopy, it relies on a Doppler separation. So in the star rest frame, the planet moves around the star, and the lines that are, or the absorption lines coming from the atmosphere of the planet, they will have a radial velocity shift. And this shift can be then, well, using that shift, you can extract information about the atmosphere from that. It's usually done with high resolution spectrographs on ground telescopes. And it is, I've said it here, it does not have so much information because it's mainly very good for detections. So if you want to find a species, then it's super good because it's very robust at doing detections, but it does not have as much information content as transmission spectroscopy, which relies on a physical separation. So you wait until the planet comes in front of the star, and then you can look at the light that is filtered through the atmosphere of the planet. This is mainly done with space telescopes, and it has more information. What do I mean by this? The result will depend on the temperature of the atmosphere, the composition of the atmosphere, but also the gravity and some other factors. So there's a lot of parameters that influence the transmission spectrum, but it's less robust because you have so many parameters. It can be also more degenerate. So if you have data of lower quality, then you will have very degenerate solutions. So a little bit more about transmission spectroscopy, which is what I will focus on. As I already said, if you wait until the planet comes in front of the star, the light will pass through the atmosphere, and depending on the molecules in the atmosphere, some will be absorbed and some will be transmitted, making the planet appear bigger or smaller. And this can be seen in the light curve. If you have the planet, it passes in front of the star. Depending on the wavelength you are looking at, the light curve will have a bigger dip, so a bigger transit depth or a smaller transit depth. And then you can plot basically the size of the planet or the depth of the transit with respect to the wavelength, and then you have a transmission spectrum. So it's actually not a spectrum in the true sense of the word, because you're not measuring flux, but you're measuring the size of the planet or the transit depth in function of the wavelength. And this is what it looks like. We have a little bit of a problem for the wavelength for transmission spectra, because the most prolific instrument to do these kind of studies, I guess, is Hubble, the Hubble Space Telescope with Wide Field Camera 3, but it has a very narrow wavelength range here, as you can see. And then, well, you see that this is actually a quite good signal, quite clear, and this corresponds to absorption by water vapor in the atmosphere. However, we would like to have some more information, because in this wavelength range, there is not much else to see than water vapor or maybe some clouds. So we can continue more towards the visible. And then it looks like this. You have some other instruments here. And you see that the scatter towards the visible becomes much bigger. And you do get some information about here sodium and potassium, who have very big lines, but not much else, because the most of the molecular signatures will be more towards the infrared. And towards the infrared, we see that we have, well, we are basically blind. We have these two Spitzer data points and not much else. So there is a problem for transmission spectroscopy with respect to the wavelength range, and we would like to continue more in the infrared. So we need, of course, other telescopes for that, and I'm thinking mostly of the James Webb Space Telescope. There's also another problem, that is that it's potentially problematic to combine data sets, because there can be slight systematic errors in the reduction of the data, and then that can give an offset, and then it's difficult to combine these. But as I already said, the James Webb Space Telescope would make a huge progress in that respect, because then we have a wavelength coverage up to 28 microns, so in the far infrared, where we will see all kinds of molecular signatures, hopefully. Then there's another obstacle, now more towards the modeling side, because of course, if we eventually have this nice new telescope, we also need the models that are good enough and accurate enough to explain the data. And for the modeling, what I'm working on, there's an obstacle that tidally-locked exoplanets are three-dimensional. So what do I mean by this? Is that they can usually be assumed to be synchronously rotating. So the rotation period is equal to the orbital period because they are so close to their star. And that means that the same point is turned towards the star the whole time. So they have a permanent day side and a permanent night side. And this actually acts as a kind of heat engine, where the irradiation from the day side is the hot source, and then the night side cooling is the cold reservoir. And then this gradient, it acts to drive the heat engine, and the heat engine is the atmosphere. And it produces work, and the work is here manifests as the circulation in the atmosphere, so the climate with all kinds of wind movements. One of these is a quite robust outcome of climate models, and that is an equatorial jet stream. So it's not a jet as we sometimes are used in astronomy, like something that goes away from the object, but a jet stream which goes around the planet. And this, this equatorial wind is really going around the whole planet towards the east, and this tends to homogenize the heat, the temperatures, and also the composition a little bit. And then also quite recently, interestingly, the first observation of a chemical gradient in exoplanet atmospheres was found, and that this happened in the ultra-hot Jupiter WASP-76b. So this planet has a day-side temperature that is hot enough for iron to evaporate. So there was a detection of iron in the gas phase. And this iron is then transported through wind towards the back of the planet, towards the night side. And there the temperature is colder again, so it condenses out of the atmosphere. There was no iron detection anymore on that side. And so it's a planet where it literally rains iron. And this is the first observation of a chemical gradient. So all of these effects, they really act to show that exoplanets are truly three-dimensional objects, and that it might be needed to take this stuff into account. So the question that we can ask ourselves is then, do these multi-dimensional effects matter when we do atmospheric models? What do I mean by multidimensional effects? So a little summary again. So it can be the temperature between the two limbs. If we look at the planet in transmission spectroscopy, then we are probing actually the outline of the planet. So the separation between the day side and the night side. So if there's a temperature difference between the two limbs, then that can be important. There can also be chemical compositional differences between the limbs of the planet. And also mixing, of course, can happen in the vertical direction, which is still in principle a 1D effect, but also in the horizontal direction. And then it becomes a 2D or more D indeed. And then, well, the likely answer to this question is that, well, these effects do matter. Right now, we don't really have enough data or good enough data to break the degeneracies in these models. But in the future, we hopefully will, with the advent of the space telescope, of the James Webb Space Telescope, and also the Ariel Space Telescope a little bit later. And I'm, of course, not the only person thinking about these multidimensional effects. There have been many studies already done on this front. And I list a few of them here. But usually they focus, because these models tend to be a little bit more computationally intensive than more simpler 1D models. Usually they focus on a few different case studies. And I was asking myself the question, well, for which planets in the whole diversity of exoplanets that we know, for which planets do these multidimensional effects matter a lot, and for which maybe 1D effects can be suitable. So then we set out to synthesize a grid of 144 irradiated exoplanet atmosphere models. And I will show you the results of that right now. Well, first I have this slide on the methodology. So it's quite a lot, I guess. So, but if you have questions about it, you can always ask me afterwards. But I will quickly go through how we set out to synthesize these models. We start by computing a radiative equilibrium. So this means the temperature that the planet would have if there was no atmospheric movement, basically. And this is done with the radiative transfer code. And then this radiative equilibrium, why do we compute it? We use it actually as a reference state for the climate code. So this is 3D GCM, a general circulation model, or a climate code, basically. It's a hydrodynamics code to simulate the atmosphere. And the code is allowed to evolve towards this equilibrium state on a certain time scale. And then it reaches a certain steady state. And then this gives us 3D information about what the temperatures and the wind speeds should look like. And then these temperatures and wind speeds, they are both used to calculate the chemical composition of the planet. So that's the next step. The temperatures are, of course, used for the reaction rates of the chemical reactions, and the winds are used in order to be able to simulate the mixing. So the code that we used for that is a chemical kinetics code, and it's a 2D code actually. The dimensions are the vertical dimension, which we always take, of course, and then also the longitude dimension. So it's basically an equatorial band around the whole planet. And then this gives us the chemical composition. And finally, we use yet another code to compute a synthetic spectrum from that. For the grid, we have taken 4 different stellar types, 3 different gravities to basically probe the whole diversity of potential surface gravities in the known exoplanet population, and quite densely spaced temperatures. So we have 12 different temperatures going from quite cold to rather hot exoplanets. Now you can ask yourself the question, why are we taking 4 different stellar types? Is that so important what the stellar type is for the planet? And well, the answer is, well, actually, I do not necessarily want to vary the stellar type of the model, but the rotation of the model, because all of these models assume synchronous rotation. So if you put 1000 Kelvin planet around an F star, you will have, of course, you will have the planet at a much bigger difference, and the rotation period and the orbital period, which are the same, will be longer. But if you put it at an M star, you will have it at a very short distance, and it will be a fast rotator. So by varying the spectral type of the host star, you can actually, in a more or less self-consistent way, vary the rotation period of the planet. And that was also one of the things that that we set out to do, is to look at the effect of rotation on the climate and on the chemistry. So here is a typical output of a climate simulation. So the typical climate of a hot Jupiter. What you can see is this is kind of a world map view of the temperature. So you have longitude at the bottom, and then the y-axis is latitude. And the substellar point, the point turned towards the star, is here in the middle. So the day side is going from -90 to +90 degrees, and the night sides are on the outside of the plot. And you can see that here the terminator regions are the dashed lines. So these are the ones that are probed in transmission spectroscopy. What you can see is that the arrows, which represent the wind speeds, they really show that this equatorial jet stream that goes around the planet is present. So you have a fast kilometers per second jet stream that goes all the way around the planet here, always pointing towards the east. And you also see some heat advection here, where you see that the advection from the heat from the day side is advected towards the east, resulting in here a terminator or a limb that is hotter, and here it is colder. So this is already important when we are going to synthesize our transmission spectrum. Now I show you a whole lot of these plots. So this is a subset of the grid, basically, where the models are plotted with irradiation increasing downward. So you can see the temperatures here on the left, and also for the different stellar types. So the rotation is actually increasing towards the left as well. And then, of course, it's a very dense plot. I don't want you to look at everything that there is to see, but I'll just tell you a little bit about the trends that we find. And that is about the day-night side temperature difference. So you can see that the difference between the day side temperature and the night side temperature, it tends to increase with irradiation and with rotation. So with irradiation, it makes sense, I think, when you look at the colors here. The day side temperature goes up quite a lot, whereas the night side temperature, well, it remains more or less cool, so the difference will increase. And also with rotation, this is easiest seen, I think, somewhere around 1800 Kelvin here, where you have, for slow rotating planets, you have quite some heat advection and not such big contrasts. Whereas if you have a very fast rotating planet, then your day side and your night side will have very different colors, resulting in different, well, in asymmetry, of course. So the heat redistribution is apparently climate dependent. Then the day-night side temperature difference increases with irradiation and rotation rate. Now, there's good news that we can also have some observational constraints of that. So this is here a plot of, for different exoplanets, this day-side, night-side temperature contrast plotted with respect to equilibrium temperature. So you can see indeed for hotter planets, this contrast increases. So that is in agreement. Now, we can also do it for the models in our grid. And then you can see the same thing for the effective, if the effective temperature increases, the day-night side contrast increases as well. And this is plotted again for the different stellar types. You can see consistently the M types are at the top, which means the fast rotators are there. So then the contrast increases as well. This also has an effect, so the rotation rate, it also has an effect on the equatorial jet stream, and also the speed of the jet stream and the shape. So here are again 3 models plotted. Now, what is shown is the wind speed, so in meters per second. So you can see that this is really a kilometers per second magnitude. And it's averaged over the whole longitude of the planet. So here, this is the latitude, where you have the South Pole, the equator, and the North Pole. And this is the altitude in the atmosphere. So you can see the bright blue blob in the middle is this equatorial jet stream that we are talking about. As the rotation rate increases, it seems that also this equatorial wind speed increases as well. For slow rotators, it's quite low. For fast rotators, it's quite high. And the jet stream becomes narrower as well. And even for the very fast rotators, you start to see banded structures like that. So with one in the middle, and then two in the opposite direction, and then on the low latitudes, then for the high latitudes, again in the other direction. So there is some theoretical basis for that because it represents a transition from a dynamic regime where rotation is dominating the climate to a radiative regime where the irradiation and the day-night side temperature differences are, or the irradiation on the planet is dominating the climate. And this is also important as the input for the chemistry models, because this will have an impact on the amount of horizontal diffusion that we have in our chemistry, or horizontal advection. And then we continue to our chemistry models to see how this horizontal dimension influences the chemical composition. And then I show here some different plots of different molecules in an exoplanet atmosphere. Here's their abundance on the x-axis, and on the y-axis you have the altitude in the atmosphere, or the pressure, but it's inverse, so that means that it's the height in the atmosphere. And we plot different lines for corresponding to different locations on the planet, as I try to illustrate here with this little figure. And you can see that for species like water or carbon monoxide, it appears that there's no difference where you are sampling on the planet, because all of these lines, they end up on top of each other. But for methane, there is. And you can see that depending on where you are on the planet, your methane content will be here quite high or quite low. But this is for a model, well, this is actually a collection of one-dimensional models. But if we now also introduce the second dimension, which is introduced with this horizontal wind speed here, which I've put to 0 here, then we see a different figure, where all of these lines corresponding to different methane abundances are squished together, they are averaged out, and every part of the atmosphere will have also the same methane abundance. So this, as you can imagine, this will also have an effect on the transmission spectra. And then here I show you again a very big plot with a lot of these, a collection of a lot of these plots together for a subset of the grid. It's again in the same format. The radiation increases downward, and the rotation increases towards the left. And there is again a lot of stuff to analyze here, of course, but I just show you again to the big picture. And that is, to me at least, there is a striking dichotomy between, on the one hand, the cool planets, and on the other hand, the hot planets, where the cool planets tend to be horizontally homogeneous, and the hot planets tend to show large, or at least very noticeable differences between the day side and the night side, or longitudinal composition differences, basically. So this is quite interesting. Now let's then do the final step and have a look at the transmission spectra corresponding to all of these models in the grid. And we do this by combining contributions from the both limbs. So here we take an approximation that the one model here corresponds to the half a disk here, and then one model here corresponds to half a disk on the other side. And we can plot, of course, also the transmission spectra for both separately, and then you can already see a difference, but it's very difficult to probe them separately, but because usually you probe them both at the same time, unless you are doing some very fancy observations where the planet is just in the beginning of the transit, where you probe only half of the disk, but that has not been done before, I believe. So the transmission spectrum that you will see is actually the average of the two, and that's here plotted in gray. And then we can actually plot the transmission spectrum for a range of different a complexity or a hierarchy of different model complexities, as I will show here. So you can first start with the simplest case, which is a sort of agnostic one-dimensional average. So you just take the average temperature of the planet. You can model a one-dimensional spectrum for that with equilibrium chemistry. Then chemistry will look like this. And then the spectrum will look like this. So here, well, if you're not used to looking at these spectra, I can maybe give a little bit more information about it. Here you have all these wiggles are typically water absorption bands. And then here at the end, you can see some more molecular features of other molecules. Like here, this bump can be attributed to CO or CO2. And if you do this for cold planets, you will, instead of water, see mostly methane. They are methane dominated. Okay, if we then continue and we do an increasing model complexity step or level, then we can, for example, introduce temperatures that are coming from the climate model and still use equilibrium chemistry. Then you can start to introduce differences between the two limbs, of course, where you have on one hand a cold limb where you have apparently quite a lot of methane, and on the other hand you have a hot limb where you have a lot less methane. And then just by taking the temperatures from the GCM and still using equilibrium chemistry, you can already see that the spectrum has changed quite a lot, and the depth of the bands has reduced mostly, and yeah, and well, the same signatures are there, but the depth of the signature has changed quite a lot. Then a next step could be to introduce 1D chemical kinetics. So you take vertical mixing into account, and then you can see that vertical mixing in the atmosphere, it acts as a homogenization in the vertical direction, where at some point the chemical reactions are not fast enough, and then the dynamical regime takes over, mixes the atmosphere, and the rest of the atmosphere will have a homogeneous composition. And if you do that, you can see that you arrive here at quite some methane for both limbs, and this is visible here in the spectrum. This peak can be attributed to methane absorption. And then finally, you can introduce again the horizontal direction. You can see that then the chemistry changes a little bit more, and the spectrum again changes. Now the changes are not so big actually for the model that I've chosen here. The 1D chemical kinetics model already did quite a good job at representing this, but you can still see certainly differences between all the four spectra. Then we can also have a look at different models, do the same, well, we can do this analysis for every model in the grid, of course. But if we then do the comparison between a cool planet and a hot planet, then we can start to draw some conclusions. So for a cool planet, this is the step including everything. So just the last step that I show is you have, again, as I mentioned a few slides ago, that cool planets tend to be horizontally homogeneous. And you see that they are here. And if you plot all the spectra on top of each other, you see that the final spectrum, which is here in green, it overlaps quite well with all the previous spectra except the first one. So there you can argue that if you know the temperatures at the limbs. So a 3D GCM is still quite useful to know the amount of heat redistribution and the temperatures at the two limbs. But if you know that, you can already have a good guess at the spectrum well, by using that information. On the other hand, for the hot planet, they are not horizontally homogeneous, as I said. So, well, they are in H2O and in CO, but in the other molecules, they have differences between the two limbs. And there, each spectrum is really looking quite differently from the other. For example, here in this wavelength range, you can see that this is also the wavelength range where methane absorption will be. And then if you use a 1D model, you will either have a very high water absorption here or a methane absorption here, whereas you use the full final 2D model, you will have here, again, less methane, as you can see also in this plot. All right, so these were just a few samples from the grid. And then I think we can go to some take-home messages of looking at these kinds of models. And that is that exoplanets are inherently three-dimensional. I hope I've managed to convince you of that. So the day-night, the different day-night states, also the different states between the two limbs of the planet, the wind dynamics and chemical quenching can alter the observables a lot. There is seems to be a striking dichotomy in a degree of chemical homogeneity, where the cool planets tend to be chemically homogeneous, and the hot planets, they tend to show quite significant differences depending on the longitude where we are probing. Then the rotation rate, it has an effect on many different levels, on the heat redistribution, as we have seen, where the day-night difference, temperature difference was quite high for fast rotators, but also on the horizontal wind speed, and also on the vertical mixing, which I didn't mention actually in this talk. And then finally, you can ask yourself the question, is a 1D model an appropriate choice for the planet that I want to model? And it's difficult to answer that. The answer will be, it depends on the planet. But in general, it seems to be for cold planets, yes, if you are taking into account accurate temperatures at the two limbs and also vertical mixing. And I think that that was what I wanted to tell you.
Thank you, Robin. That was very enjoyable. Thanks. Are there any questions? If so, let me know in the chat and I will call out your name. Yes, please, Luc.
Hi, Robin. Thanks for a very interesting talk. I was wondering, you said that the rotation of the planet, if it rotates faster, it would be more, or yeah, the day-night difference would be higher, right? Yeah, indeed. And so I think this is quite counterintuitive. Could you maybe explain it a little bit more?
Well, it's okay. It might be counterintuitive, but I think it's all very difficult to have any intuition for that. The reason is, or one of the main reasons is that the climate type changes with faster rotation. And well, I can maybe show you some extra stuff on that. So here I have the same figure that I showed earlier, but I try to assign some climate regimes to that. And you see that for slow rotating planets here, you get equatorial superrotation quite often. So for all of these, which is denoted by this arrow. But for faster rotating planets, you get also retrograde flow. So what do I mean by that is that not only on the day side you will have this wind towards the east, but you will also get a component that is westward. And that actually, well, serves to disturb a little bit the efficient heat advection towards the night side. And I think that this could be a part of the answer to that. But well, in principle, it depends on, yeah, the heat advection depends on the winds, which depends on a certain balance between the pressure gradient of the temperature, the pressure gradient caused by the difference between cold and hot air parcels, and also the Coriolis force. So if you start tweaking the Coriolis term, then you will in the end have different wind types, and that actually serves to have this difference. But yeah, it's different to have an intuition. It's difficult to have an intuition for it, that I feel myself, but yeah.
Thanks.
Okay, then we have Pierre is next. Pierre, you might still be muted.
Yes, no, I was not muted, but my internet connection is very bad. Sorry. At the end of the talk, you showed the number of vertical profiles, and I was wondering if you do not expect what could be the role of photodissociation actually in the higher atmosphere.
Yeah, okay.
Because they were all very vertical and not changing anymore, and so I'm wondering what the effect of photodissociation is.
Yeah, indeed. I can go back to some. So I can. You mean, for example, here in the higher altitudes?
Yes, exactly.
Yeah. Well, photodissociation is currently not included in my chemical model. And the reason is that I am using a chemical network which is not optimized to accurately represent photodissociation. It's a reduced chemical network, so it's good to easily simulate a lot of models, such as this case in the grid. It is expected, however, that photochemistry will play a role, indeed, in the higher altitudes mostly. Now, we are not very high in the atmosphere, and most of the radiation, most of the contribution to the transmission spectrum comes from the layers here around the 10 to 100 millibar, something like that. So around this level. And in general, photochemistry will play a role on higher levels. However, in general, also photochemistry will play a bigger role in colder planets. So indeed, it's a very good remark that this is something that is currently not included. And I also have plans to include this effect in a later stage, indeed.
Okay, then I'll go first for the younger person, Yannis.
Yeah, thanks, Robin, for the presentation. I was just wondering, in all your plots of wavelength versus transit radius, you cut it at 12 microns. Is there nothing to be learned from the region of 12 micron to 28.8, I believe is the MIRI range?
Yeah, indeed. Yeah, the reason why I did that is because it will be, it's less clear actually. Because as you can see, yeah, it's not noise, of course, it's signal, but the oscillations basically, or the absorption bands that you start to see there, they all become very noise-like and also flatter. So it will be more difficult to see something there, but
and that extends to, yeah. Okay, so, yeah, thanks.
Okay, Luca?
Yep. Hi, Robin. Thank you for a very nice talk. I had a question. If I understood correctly, when you compose the spectrum, you take small or thin ribbon along the equatorial plane. But when you actually do an observation, then it's not a small equatorial plane, but you get a full contribution from, like, how many degrees it will be, 180 degrees along the limbs.
Yeah, indeed.
And chemistry, I would guess, will be different because you have different kinds of flows. You don't have equatorial jet anymore when you go to the poles. How will that affect your spectrum if you take the full contribution from the limb and not just a small point?
Yeah, Okay, thanks for that question. Well, you see that indeed what we do is we take basically the situation at the equator and we use that as more or less the half of the disk. And indeed, that is not totally correct. There has been some other research done to incorporate all of these different parts. And it has shown that it can indeed have an effect of this on the transmission spectrum. And there's also been some other research done to model the advection from, for example, the equator towards the poles and vice versa. And that can also have an effect on the chemical composition. How big the effect is, well, it of course, again, depends on the type of planet. For hotter planets, I think it's, at least in the chemistry department, I think it's a very good approximation that I'm using now to just focus on the equatorial band, because there, with respect to the chemical composition, not many differences are seen. For the colder planets, it might be a bigger problem, but that's difficult to know actually. And for the spectrum, there is something else that we can do to make this approach more accurate, and that is to really divide every part of this up and calculate the different contributions in order to arrive at the final transmission spectrum. And this will be definitely well, this will likely be an improvement, but there is also reason to assume that the equatorial region will dominate anyway, because it tends to have the hottest temperatures and therefore the most contribution towards the spectrum.
Okay, thank you.
Okay.
Okay, Jordan.
Hi, Robin. Thank you for your nice talk. I have a question on your 3D global circulation models of your hot Jupiters. Yeah. Do you take into account tidal deformation or any possible tidal deformation of your hot Jupiters, or does it assume sphericity? And if so, if you take it into account, if you don't take it into account, how much do you think this will affect the outcome of your models?
I do not take it into account. It's really a spherical model, and yeah, I'm really not sure what effect it would have if you have a deformation, because indeed these planets are quite close to their star, so you could expect some tidal deformation. On the other hand, they are synchronized as well. So I'm not, yeah, I don't have an idea on whether that would give you a deformation that will be so significant as to alter the atmospheric, well, to alter the climate. So not sure.
Yeah, me neither. So thank you.
Yeah, thanks. I will think about it.
Okay, Jacques.
Yeah. Hi, Robin.
Hi.
I have a question because I remember well you mentioned in the introduction that you can constrain the formation scenarios of the planets by studying its atmosphere. Mm-hmm. I would expect that you can constrain that by studying the bulk composition of the planet and not the atmosphere, because as you showed, the irradiation and rotation, and I believe other parameters can influence already the chemistry of the atmosphere. So how can you constrain the formation scenarios?
For the formation, indeed, you well, it will have to come from detections, indeed, of the bulk, probably of the elemental ratios that make up the air mixture of the atmosphere, and then it will be dependent on, for example, things like the carbon to oxygen ratio. If you have a protoplanetary disk, there will be a gradient in the carbon to oxygen ratio. So if you can link that existence to a certain type ratio in the atmosphere to the protoplanetary disk, then this can give you some information about that. But yeah, then indeed you have to take into account, well, you have to assume that the planetary, that the atmospheric composition is somehow representative to what is beneath that, of course. So there, well, you also need interior models for planets and stuff like that.
Do you think it's a fair assumption to do?
No, I don't think so. But I think you will need some good planet formation models and interior models as well in order to have a handle on what fraction of the material will stay in the atmosphere and what will maybe condense down or something like that. Yeah.
Okay, thanks.
Okay, then we have Matthias.
Yeah, thanks, Joris. Thanks to you too, Robin. My question was actually probably a bit more basic, or I overlooked something. But you mentioned that you sort of mimic rotation by changing the stellar type, right? So taking a lower mass star to bring the planet closer. But then, how do you vary the equilibrium temperature? Because in my naive interpretation, at least, a star of fixed stellar type will not suddenly become hotter, right? So how again do you set up that grid and specifically the temperature ranges?
Yeah. So I will go back to it. So I will, in principle, I fix the equilibrium temperature beforehand. So I know the equilibrium temperature of a planet that I want to have in my grid. Mm-hmm. And then I compute at what distance I have to put that planet, right, in order to achieve this this temperature. Okay. And then the distance will be dependent on the stellar type, and that will self-consistently change the rotation period of it.
Okay, yeah, that makes sense. So for the F star, for example, a hotter planet will have a shorter period naturally, because you compute beforehand what the distance has to be, and then you assume synchronicity. Yeah, that makes sense.
Yeah, indeed.
Okay, and then last but not least, Hans.
Yeah, thank you. So I have a question with respect to the JWST, because that is the deadline is next week, I think, or at least for the first round. Are you involved in one of the projects? Just
I am involved in some projects, but not as a PI, because I try to focus on writing the paper right now for this research.
No. Yeah, but then I have a question, because if I look at the spectra, I think let's say the differences between the different models, which are quite vastly different, but the result on the spectrum is quite subtle.
Yeah.
Say you compare the spectral comparison between models which are physically quite different, but the impact, so the observable on the spectra, in my opinion, is very subtle. So how do you think, is that a question of being very, very, very accurate with the observations, or is there a gap between the intrinsic content of the observable and the complexity of the model?
Yeah, I understand your question, and actually there is indeed a gap, because we are working with indeed complex models with more dimensions, but in principle the maximum amount of dimensions that you will see is 2, because you are looking at a projection of a disk for that transits the star indeed. So you will always have some loss of information just by the technique that we are using. Yeah, that is correct.
Yeah, and so at the end, of the day, I think it looks like that the observable is too simple, or at least, I mean, the complexity of the model is not represented by a huge difference in the spectrum, which is then the observable to be used to constrain the model. So will that not be a problem with respect to the quantified interpretation of a spectrum?
I don't know if it will be a problem. I know that, I know that already studies have been done to do retrieval analysis, so to get the
Yes.
the parameters outside of the spectrum, and doing comparisons between the 1D models and for example retrieval of 2D models, and there when you really use retrieval analysis and Bayesian statistics, you will see that the use of simpler models can definitely bias the parameters that you get out of it. So I think that,
okay,
well, there is indeed a balance to be struck there, but I think that 1D will really be too simple.
Yep.
But even though I agree that the differences can sometimes be quite subtle, indeed. That's why we need we will benefit a lot from the long wavelength ranges.
Yeah. Okay. Thank you.
Okay. I would like to thank Robin again. Thank you very much. I would like to thank everyone for joining, and I hope to see you again next week, the same day, same time slot, to listen to the seminar of Romain Loquier. So see you then. Bye.
All right.
Okay.
Thank you.
Bye.
Bye.